All right, Calc BC, I just wanted to give maybe two other just quick examples of the direct comparison test here. So something real quick just to look at. So take a second, look at the series that I've given here, and make a first guess as to converge or diverge. Converge or diverge. Now I hope, as you thought about this, you say diverge. So the reason is that what we could probably say is that this piece doesn't matter a whole lot, right? It's some value between 1 and -1. And so as n grows to infinity, this is really a lot like n over n squared, which is 1 over n, which is the harmonic, which diverges. So the first thought here is that this probably diverges because it's really just kind of like the harmonic. You might again think, wait a minute, isn't it? I'm subtracting something, isn't it approaching that zero faster? And remember that the rate of growth of the function won't be any different, right? It's not going to be this part that's going to be affecting that pattern back down to zero. Even putting some other, it's the same thought as like if I would put a -10 in here instead, or even, this can be any number, and that eventually this term matters so much more that's not going to be the limit. So, but that's really informal to sit there and go, well, it's kind of like the harmonic, so it diverges. Now, if this is on like a multiple choice on the AP exam, like I would probably just pick diverge and go on. Like I wouldn't probably do a lot more with this. But if we think about the logic, so the logic of this direct comparison test, what we would like then to show is that this kind of generic term, and if it's kind of like the harmonic, and I know that the harmonic diverges, if this is bigger than something that diverges, then it should diverge, right? So bigger than divergent is divergent, smaller than convergent is convergent. The other two scenarios you can't tell, and we'll have to use a different test. Well, oh wait, actually, aren't we done? Take a few seconds, think about why is it, even just at this moment, you should go, oh, that makes sense. So I hope you decided that notice that this cosine term, cosine squared of n, is always greater than 0. And if that's the case, we are making the denominator smaller, which then should be making the fraction bigger compared to n over n squared. So if we would say, like, this is definitely true then, that n over n squared must be smaller than this fraction, but wait, this is actually equal to 1 over n, and if that diverges, we are bigger than divergent. So there's a quick example of comparison. Again, harmonic is a really common series that we'll use for comparisons. Okay, another quick example here. So here's a series. Again, you can plug in 1, 2, 3, 4, add them all up, et cetera, dot, dot, dot. And so if I would say convergent, divergent, I hope in like 5 seconds you should be able to make a really strong argument that you think this should converge. Effectively here, that we have something like 1 over n squared, right? Like we could make that argument of the +2 and the +5, this is the horizontal asymptote conversation, don't have that much effect on it. But if we're going to try to be a little bit more precise with it, let's think about how we could maybe manipulate this. So I'm trying to show that if I already think this converges, then I need to think about this term I would like to show is smaller than something else that I know I would know converges. And so that thing that we're really probably comparing this to is 1 over n squared. Okay. So again, I hope kind of looking at this that we could make some statements and say, okay, this n squared plus 2 over n to the 4th plus 5 must be smaller than n squared plus 2 over n to the 4th. Okay, so I'm going to really remove that plus 5, which means if I was adding something to the denominator, that should have made that fraction smaller, so that's why I'm saying that this is larger. Okay, but this is actually equal to n squared over n to the 4th plus 2 over n to the 4th. See that? So I'm just like thinking about splitting the fraction, right? A plus b over c is a over c plus b over c. I'm just doing the addition basically backwards. Oh, wait, this is actually equal to 1 over n squared, and this is 2 over n to the 4th, and both of those we know are convergent. And if you add two things that are convergent, they're convergent, so this thing is smaller than something that's convergent done. Okay. And again, that's really why we had that p-series test that I wrote. And so I'm finishing with this thought. So this 1 over n to the p, as n is going from 1 to infinity, and so if p is greater than 1, we have convergent. And that then actually applies when we just look at something like this. So there's just two quick examples when we think about comparison. So I need to be bigger than divergent, and then I'll know I'll diverge, or smaller than convergent, then I'll know I converge. But in the other two, if I'm smaller than divergent, I don't know. If I'm larger than convergent, I don't know. Okay, so more on different tests tomorrow.